Bismillah ar-Rahman ar-Rahim. Today we are going to start a new unit, which is about registers and counters. And these two components are essential for digital systems, and they are used, very widely used in digital systems. So we are going to, in addition to seeing how they are implemented, okay, using flip-flops, we are going to also discuss some of their applications, okay? So registers and counters, and then the unit is over, and then we have also one more final very long lecture, and then the whole semester is over, okay? So let's start with registers. Basically, we have registers, usually a register. When you say a 1-bit register, it's nothing but a D flip-flop, okay? A 1-bit register is actually a D flip-flop, okay? When you have more than 1-bit register, like for example, an N-bit register, then the input will be an N-bit D input, okay, external input. The D now is more than 1 bit, okay? And the output is more than 1 bit. It's the same number of inputs and outputs. And the function table, as shown here, is that, I'm assuming positive edge triggered flip-flops, that when you have a positive edge on your clock, then Q will get D, okay? It will get D. Okay, so Q is in bit and D is in bit. So it's a perfect assignment here, okay? It's just an assignment that happens during the rising edge of the clock, okay? Otherwise, if there is no rising edge of the clock, then Q of T will be Q of T minus 1, which means no change, okay? If we would like to design this using the design procedure that we learned last time, then we will have to deal with 2 to the n states, because we have n bit. 2 to the n states is a huge number, okay? It's a huge number of states. For example, in the Intel processor, for example, the Pentium, current Intel processors, okay, they have registers of size 64-bit. So imagine to deal with 2 to the 64 states, literally a humongous number, a huge number, okay? So there is no way for you to track the state diagram of this size, okay, of size 2 to the 64. So you have to revert back to ad hoc techniques, similar to the techniques that we used when we developed iterative circuits for comparators and adder circuits and stuff like that, okay? So let's see an example of how we can use ad hoc design to design or to implement a 3-bit register. So we would like to implement a 3-bit register, okay? So a 3-bit register, okay, as you all know, must contain or must have 3-bit or 3 flip-flops, 1 bit for every flip-flop, all right? So we have 3 flip-flops like this, and they all have to share the same clock, okay? They are all synchronized with the same clock. And each one of them have 1 bit of the input. So this is for D0, and it outputs Q0. And this is for D1, and it outputs Q1, and this is for D2, and it outputs Q2. All right? So this is a 3-bit register, in fact. And if you want, you can also have an asynchronous reset, so that you basically can reset your flip-flop regardless of the clock. You want to have an initial value of your register. This is reset, and this is the same signal reset. So they are all connected to the same line, just like the clock, okay? The clock, it has the same name. So it must be the same signal, okay, the same wire. All right, any question here? So this is, instead of going through the state diagram and then converting it to a state table, and then take the derive the K-map for every next state and output, okay, and then draw the circuit. I mean, this is this design technique, which is an ad hoc design technique, is based on our understanding of how the flip-flop works, okay? So we know that this will work for sure, okay? But let me ask you a question. If you would like to design, just this is an information check for you, okay? It's a checkpoint to see whether you are following or not. If you would like to design your 3-bit register using our design technique that we discussed in the previous unit, which is the design procedure for clocked sequential circuits, how many states do you need for that?
8.
Anyone? I just asked the question, guys. Did you get the question?
Yes, how many states?
Yes. Yeah. So can you answer this?
2 to the 3, which is 8, I think.
Yeah, 8 states. Excellent. 2 to the 3, because we have 3-bit. So 2 to the 3, you have 8 states. So imagine dealing with 8 states in your state diagram versus or compared to, okay, this ad hoc design technique. Okay, this ad hoc design technique is very simple, in fact. Okay, and you don't need to go over all the steps of design procedure in order to derive this simple circuit. Okay, because eventually you'll get very simple design. Okay, but I mean, you should get a design similar to this if you go over the design procedure. Okay, now let's take it one more step further. Okay. By the way, you can have also what we call you can have package your register inside. So this is 3-bit register inside the block, a black box. So this is D2, D1, D0, and this is my clock. Okay. And this is my Q2, Q1, Q0. Okay. So this basically symbol can be used in order to denote or simplify my bigger circuits later. Okay, and it also have a reset as well. Okay, reset input that will reset all the bits. Okay, this is clock. I just don't like the shape of the C here. Okay. Looks like a G. I have to make sure that it is C. Okay. All right. Now let's take this a step further. But we would like now to have a parallel load to our add a parallel load with parallel load enable input. Okay. So in addition to being able to, so what's the problem with this now? What's the problem with this design? The problem with this design that every clock cycle, every positive edge of the clock, we will have to load the content of D into Q. And this seems to be too much for us. We would like to have some control, some load control to enable or disable the loading. We don't want to always enable the loading, okay? So instead of loading D, I would like to be able to load Q sometimes. So loading Q means I do not change my value, okay? So how to do that? This is the function table, basically. This is a function table. I'm also including the enable input, which is the load enable. So in a positive edge, and my enable is 1, I'm going to have my Q will be, or my D will be loaded into Q. If enable is 0 with a positive edge, then my Q will maintain its old value. There is no change here. If there is no positive edge, then regardless of enable, my value will not change. Okay, so this is the function table. All right, is this clear? Now, how do we implement this? Basically, it's the same as this one, except that at each input here, we need to decide whether we take D0 or Q0, depending on enable. So if enable is 0, I should pick Q0, and if enable is 1, I should pick D0. Right? So what does this ring a bell? What do you think we should use?
It's like if condition, we use multiplexer.
Excellent. Yeah. So multiplexer with the select line being enable. So if enable is 0, I should load Q0. And if enable is 1, I should load D0. And the same goes for all of the inputs and outputs here. Okay. So this is how it's done. So Q0 when enable is connected to line number 0 of the mux, 2 to 1 mux. And D0 is connected to line number 1, and enable is the selection line. Same for all of them. Okay. Do you see that? And this is the block diagram, or the black box representation of this. And I forgot to write down the name. So with enable here, with enable, load enable. Yeah. And I also forgot to have the reset. Okay. So most of the time, reset is very important for your for validation. Okay. You want to be able to start from a known state and then test your circuit. Okay. So reset will give you this ability. Any question about this? Is this clear? Okay, let's move on one step ahead. So what about a shift register now? Shift register, if you do remember, you can either shift left or right. Now we would like to show the implementation of a shift register using or a 3-bit right shift register, 3-bit right shift register. And this is the function table for the right shift register. At the positive edge, by the way, let me ask you this. What if I want my flip-flop, my register, to be, instead of positive edge triggered, I want it to be negative edge triggered? What do I need to change here?
I think you make a bubble in the cycle.
This one,
the clock.
The clock, yeah, excellent. Yeah, so I have to have I have to invert the clock signal in order to have it like negative edge. Okay. So if you know how to do it for positive edge, then you should be able to do it for negative edge. Okay, there is no big deal here. Okay. All right. So if you have a positive edge for the right shift register, okay, then what do? Let me just remind you of what the shift operation does. Okay, so this is basically Q2 and Q1 and Q0. Okay, and the shift is right, so I'm going this way. Okay, I'm shifting this way, so this bit will go here, and this bit will go here, and this bit will be going to serial out. Okay, and to replace this bit now, I have what we call a serial in, because I want to be able to serialize whether a 0 or a 1. I don't want to always serialize a 0. Okay, so this one will be SI. Okay, I have just given you the answer here. Okay, so in order to shift, okay, after the positive edge, the content of Q will be SI, Q2, Q1. This one will be lost, right? So SI concatenated with Q2 concatenated with Q1, right? Otherwise, if it is not the positive edge, and if it is, for example, the negative edge or a constant 0 or a constant 1, then we have no change on Q. So how do I implement this? Using using a shift register, using flip-flops, I mean. Well, again, I have to draw them in a, what we call, I'm going to draw them horizontally this time. Let me see, here D, and then Q, and then this is my C, okay? And then I'm going to copy this and paste it twice. So this is my D2, and this is my Q2, D1, Q1, to indicate the bit position, okay? D0, Q0, okay? The clock is also shared because you have, you know, synchronous sequential circuits, okay? And for D2, what do we do? Input is going to be serial in, and Q0 is going to be the serial out, right? And in between, what do we do in between?
Connect them.
For D1, for example, D1 is this, right? I load what? Q2, right?
Yes.
And for Q0, I load, or D0, I load Q1. You see that? Okay, so this is a clock, right? And you may have a reset as well. This is reset. And here I'm going to simulate this. Let us say that I have 4 clock cycles, okay? And initially, what is the content of my registers? Q2, Q1, and Q0. What is the content of my register? I don't know, in fact, right? I don't know. It's unknown for me initially, okay? But I do have, I have control over the serial in, right? So I drive my serial in to 1 and then wait for the next positive edge to occur. So at this positive edge, this one will be shifted here, and this question mark will be shifted here, and this question mark will be shifted here, right? So this Q2 will be 1, and Q1 will be something I don't know, and Q0 will be something I don't know, right? Let's say that next my serial in is 0, okay? So next, at the next positive edge, this is going to be shifted here, and this is going to be shifted here, and this is going to be shifted here, right? So I have a 0 here, and a 1 here, and what's this?
Question mark.
Excellent, yeah. And then finally, let's say I enter 1 here again. So this one at the next positive edge. Let me be consistent with respect to colors, okay? Okay, let me draw the. All right. So this one will be 1, and this one will be what? 0.
0.
Right?
Yes.
And this one will be 1. So after 3 clock cycles or 3 positive edges, my register is very well defined. I already know what is inside of my register, okay? Because I have supplied the bits. Let us say that I would like to load my register through the shifting with 0, 1, 1. I want my Q2 to be 0, Q1 to be 1, and Q0 to be 0. What is the input sequence that you should provide through the serial in every clock cycle? Where do you start? Do you start with the 1 or the 0?
Start with the 0.
With the 0.
Yes, so serial input will be 0, will be shifted to Q2.
Okay.
And you take 1 and the next clock cycle.
So Q2 will be 1 in the next clock cycle, right? We want it to be 0.
Yes. You start from the last, am I right?
Yes. You start from the least significant bit and then shift them one by one, because basically you can see that the final destination here is the least significant bit. So you should input the least significant bit first and then the last significant bit last, okay? So if you have, for example, a 5-bit register, how many clock cycles do you need to load something in it? 5 cycles, basically, okay? It's the same number of bits, okay? Okay. All right, so what are the applications? So by the way, we call this register here. Sometimes, by the way, sometimes even with the serial out, okay, we would like to have also parallel out, okay, parallel out in addition to the serial out. Okay, so I would like to observe the complete state of the circuit. So in this case, only thing that I need to do is some wiring here. So I output my Q0 and Q1 and Q2. That is what we call a serial in. So let me use serial in parallel out register. It has a serial in functionality with parallel out, as well as serial out, of course, okay? So this is a SIPO register. So let's see what are the applications of SIPO, okay? Applications of serial in parallel out register, okay? So we can, for example, have the SIPO store the result of a serial arithmetic operation that we did last time, okay? Last time we did some circuits to do some arithmetic for us. And then you remember that we are outputting the bits of the arithmetic operation 1 bit at a time. So we can use a SIPO, okay, to store for us the bits inside the register. So this is a circuit, for example, that computes x minus 1, where x is a serial input, okay, that is fed into the finite state machine here, okay, 1 bit at a time. And then the machine will output the subtraction result 1 bit at a time. Okay, so what we can do is to feed this y, which is the output of the machine, to the serial in of the SIPO. Okay, remember that we are in the arithmetic circuits, we input first the least significant bit of the input and we produce the least significant bit of the output first. So we can feed this, and then after some bits, we can see the output result here, okay? And we can see it in parallel because this provides us with parallel out as well. And we have also a reset functionality here. We can use SIPO as also. Any question about this before I move on to the next application? Okay, no questions. So we can use also the SIPO as what we call a sequence detector. Sequence detector. How do we do that? It is simple, in fact. Let me just draw a flip-flop and show you. Let me draw a 3-bit SIPO and then show you how we can do this, okay? So I'm going to draw it this way this time, D and Q. And then the clock, okay? And we can have also a reset. I'm going to copy this 3 times. Okay. Maybe I need to pull this to the right a little bit. Okay. Yeah. So this is my least significant bit, D0, Q0, D1, Q1, and D2, Q2. All right. I'm drawing the flip-flop in a reverse way, okay? So just pay attention to this. So this is the side of my input now, and this is the side of my output for all of them, okay? So I have a clock here. And I have a reset. Come on. Okay. Okay. So this is going to be my serial in, okay? And then I'm serializing. Remember, in the sequence detection, we input first the most significant bit in the sequence detection. Okay, so we are here. We first input the most significant bit and then shift it in as we go. Okay. Okay. Now let us suppose that I want to detect input. By the way, your sequence detection is now over. It's almost done. All you need to do is an AND gate for every sequence that you want to detect. Okay, so let's say that you want to detect, for example, detect 0, 1, 1. So this is an output of an AND gate that takes what? 0 in Q2, 1 in Q0, Q1, and 1 in Q0. So 0 in Q2, it means I have Q2 complement, yeah? And 1 in Q1, it means I have Q1. And 1 in Q0, it means I have Q0. All right? So this sequence, this basically, if you have a 0 in Q2 and a 1 in Q1 and a 1 in Q0, the output of this AND gate will be 1. And this will detect for us the sequence 0, 0, 1, 1. Who can tell me how I can detect the sequence, for example, 1, 1, 0. I'll detect 1, 1, 0. Which Q do I need for this?
Q2 and do the Q1 and do the Q0 complement.
Excellent. Yeah. Q0 complement. What if I want to detect 0, x, 1. X is don't care.
Q2 complement ANDed with the Q0.
Excellent. Yeah, because I don't care about Q1 anymore, right? So you have unlimited number. Each one of these is you can use the same circuit for different sequences. Okay, for different sequences. Okay, so for each sequence you only need an AND gate. Okay, do you see that? So it simplifies the sequence detection for us, but you must be able also to know how to do the sequence detection using the state diagram, because you may get a question like this in the exam. Okay, like either this, I mean the question like this, or a state diagram question. Okay. Okay, now we have what we call the parallel in serial out register. Okay, parallel in serial out register, or PISO. What is the functionality here? The block diagram. This is a PISO, for example, an n-bit PISO. Okay, it takes either a parallel load, a parallel input. Okay, the in-bit input, or it takes a serial input as well. Okay, and we have a control here, which is S. Okay, when S is 0, for example, I can show you the functionality here that we're using. When S is 0, it is a shift operation. Else, it is a load operation, a parallel load operation. It is important that you understand the functionality before we show you the implementation.
دكتور وش معنى parallel load؟
Parallel load انه يعني هنا شوف, let me tell you this. How many clock cycles did we take in order to load 101 here? 3 clock cycles, صح?
Yes.
What if I want to load it using only 1 clock cycle, all of them together in parallel? Yeah, this is what it means. This is what parallel means. It means I'm loading them in parallel in 1 clock cycle. So you either, so this basically, this register here allows you to either load in parallel all the bits or shift. Okay? Shift in some data. Okay, so these are 2 functionalities here. Okay? Okay. So we have this PISO here, a 3-bit PISO, and I have drawn the flip-flops first. Okay, and in fact, I forgot to include also the reset as well. So yeah, and the clock as well is common. Oops, too long. All right, now I have an input called S, okay? And when S is 0, I will shift in. And when S is 1, I will parallel load. So my D here, the most significant bit of the, okay, can either take its input from an external D input, D2, called D2, or a shift serial in or shift in data, okay, another input, external input. So what do you suggest to have here? Again, this is an if statement. So what do you suggest to have?
multiplexer.
A multiplexer, excellent. We have a 2 to 1 multiplexer. And this is input number 0, input number 1, and this is my S, which is connected to the external S of the PISO register. And the output of the multiplexer is connected to the D2. So here, if we have 0, then it is a shift. So I connect the 0 to serial in, okay? If it is a 1, then we connect it to the external D input, D2 here in this case, okay? Similarly for other ones, right? This is my S, this is 0, this is 1, okay? This is D1 in this case. Who can tell me what is my data line number 0? What should I put there?
D2.
D2?
Q2.
Yeah, because this should be connected to this in this case, right? But I don't have access to this one. I have access to this now. When my S is 0, I should connect this to this, right? Yeah. And similarly for this, and this is 0, this is 1. So here I have, and this is my D0. Yeah. This is serial out. And you can also have what we call the, yeah, this is a serial out. Serial out actually is all capital, both capital. Okay. Is this clear?
Yes, clear.
Okay. Yeah, I need to, so here there is a reset. I need to stop here because this is the final point that we reached with your other section, other classmates. So let me go back and see if you have any question about any of the previous. So let me go over them quickly, okay? And then if you have a question, just stop me at any point. So we started by discussing registers, and we said first of all we said that because the systematic way of designing a synchronous sequential circuit is not good for registers, we use ad hoc design techniques, okay, which is similar to iterative design in combinational circuits. And using this, we developed what we call a 3-bit register, which is basically it loads D, okay, which is a multi-bit input D, okay. It loads D every clock cycle, every positive edge. And we said that we need some control, okay, to control my D, okay. So we need a load enable so that it becomes, the circuit becomes, or the register becomes more interesting, okay. So when enable is 1, I will load, and when enable is 0, I will not load, okay. And by the way, enable here is called synchronous input, whereas this reset is asynchronous input. So enable is synchronous. Why? Because it must be synchronized. It only works, okay? It only works if we are in the active clock, all right? Otherwise, if we are not in the active clock, then it is a don't care, and the value of the register will not change. So having enable, okay, will make us some control over the value of the register. So when enable is 0, I'm not going to change the value of the register. And when enable is 1, I'm going to load the new data to the register. Okay? And then we talked about shift registers, and we gave example of a right shift register, a 3-bit right shift register. And we said that if you provide the data or the state of the flip-flops as outputs as well, then this is called a SIPO or serial in parallel out register, okay? And we actually simulated it, okay, and I show you how to simulate it. So just make sure that you know how to simulate it, because you may get questions about this in the exam. Okay. And then we talked about the applications of SIPO, and we listed two applications actually. One is to store the results of serial arithmetic operations, okay, and the other is to use them as sequence detectors, okay. When you use them as sequence detector, you need an AND gate for every sequence that you want to detect. All right. Who can tell me with a slight change of the logic here? Okay, who can tell me how can we detect? How can we design a code detector with shift registers? A code detector. Anyone? What is the difference between code and sequence detector, by the way? No one watched the lecture? Guys, I'm not going to talk about it if you haven't watched the lecture. Please go back and watch the previous lecture. It's very important to understand the difference between sequence and code detectors, okay? So anyway, if you understand the difference, then come back here and try to for example, think how can you use what we call a SIPO as a code detector instead of a sequence detector, okay? All right. And then we talked about PISO, or parallel in, serial out. And we said that you have what we call a control input, okay? That is called S. And if S is 0, we shift. And if S is 1, we parallel load, okay? And we show you, we have shown you the circuit, or the sequential circuit for the PISO, okay? Next time, we will discuss the multifunction register and how we can implement that. Okay. Any question? Let me stop recording. No questions are there.